In today's lesson, we are going to be looking at properties of quadratics. So there are quite a few properties or characteristics of quadratics that we might need to consider or that we will be looking at in various forms of equations or in identifying the key points or in word problems, whatever the case may be. So we're going to look through and we have an example that we can kind of use to kind of highlight some of these characteristics. So the first one is the axis of symmetry. And the axis of symmetry is a vertical line that passes through the vertex and it divides the parabola into two equal halves. So our axis of symmetry is right here and it has an equation of x equals -3. And if we look at this red line, that represents the axis of symmetry. We talked about how our parabola is symmetrical. It's the same on both sides. So imagine this is the line that cuts it in half or divides it into two equal parts. Now, I mentioned this before in class, if you imagine back in elementary school when you had to use kind of a mirror to trace or draw a mirror image or a reflection on the other side of it, imagine this red line is that mirror or is that piece of glass or whatever it is that you used. So you could see the image on the other side. So this line cuts our parabola in half, and the equation is always going to be x equals whatever the x value of the vertex is. Right? X equals is the equation or the form of an equation for a vertical line, and the value is just going to be whatever the x value of the vertex is. Our vertex is where the axis of symmetry and the parabola meet. It is also where the vertex is at its highest or lowest, or where the parabola is at its highest or lowest. And we can see our local minimum or our vertex is here, right at the bottom. Right. So that vertex is that highest or lowest point, or where the parabola is the highest or lowest. It is also where the axis of symmetry goes through in our parabola. Our vertex has two coordinates, an x and a y value. In this case, our x is -3 and our y is -4. The optimal value is the y value of the vertex. So let me actually go through and highlight the y value of our vertex, and that's actually called a minimum in this case. I'll go back and highlight the vertex, resolve that. So the optimal value is just the y value of the vertex. It's the maximum or minimum point of the parabola. And when we talk about maximum minimum, we're referring to the y value only, not the x value. And that's because there is no maximum or minimum for the x values. If you imagine these two arrows at the top here, they keep going out and out and they keep slowly spreading out left and right. They get wider and wider and wider and wider. And so really, there's never going to be a maximum or a minimum x value because this graph keeps on spreading apart. Our x-intercepts are in blue. We're going to label them here. So our x-intercepts, it is where our graph crosses the x-axis. Now, our parabola can have 1, 2, or 0 x-intercepts. We'll talk a bit more about that later when we look at a form particular to x-intercepts. But our parabola could have 1, 2, or 0 x-intercepts. Now, instead of calling them x-intercepts, we might also call them roots or zeros. So just keep in mind, if you see zeros or roots, it's referring to the x-intercepts. And then lastly, our y-intercept. Y-intercept is where it crosses the y-axis. Usually there's only one of these values, not two, or zero, like the x-intercepts, right? Our graph should always have a y-intercept at some point. There should be something there, or where it crosses the y-axis. So those are the key properties, the key features of quadratics that we should hopefully be able to identify, at least by looking at a quadratic. We've learned about how to find the vertex in the vertex form and things like that, which would also then tell us the optimal value and the axis of symmetry. But the main thing is, can we identify them if we're looking at a parabola? So first question, one thing to look at is each relation linear or quadratic? And when we're given a general equation, we could be given it in different forms. So we want to be able to identify what type it is. And then a helpful tip, what we should look for, if it's quadratic, x has, or the high, or say not x has, the highest exponent is 2. If it's linear, the highest exponent is 1. So if I look at my first equation, y equals 3x minus 7 to the power of 2. Well, highest exponent is 2. It's quadratic. If I look at b, y equals 2 over 3x plus 14. I don't see any exponent of 2. So in this case, the highest exponent would be 1. So it is linear. And then lastly, x squared minus 7x plus 4. The highest exponent I see is 2. Right? So I'll circle back and circle all of them. That means this is quadratic. So that's an easy way that you can kind of tell if you're not familiar with the different forms of a quadratic. The first one you might recognize because that is our vertex form. B is the equation of a straight line, y equals mx plus b. C we haven't looked at yet, but that is also a quadratic. So we see a quadratic here, or a parabola. We're given the equation below, y equals x minus 3 squared minus 4, but I am given the equation, or the actual graph. I want to determine all of the different characteristics. So my vertex I want to find, vertex is the, in red, is the lowest or the highest point. I can see it's the lowest point in this case, and the coordinates are 3, x first, and then minus 4. So my vertex is -3, oh sorry, not -3, +3, -4. And I could get that from the equation because the equation is in vertex form. So I do know that h and k is my vertex. Direction of the opening, I look where that opening is on my graph. I see it at the top, or as mentioned in class, I look where the arrows are pointing. In this case, the arrows are pointing up, so the direction of opening is up. For my step pattern, I have to go to the graph. I do have nice points here, so I can go through and do my step pattern. I start at my vertex. I go 1 to the left or the right. I go up until I hit my graph. So the first step up is 1. Do it again, go over 1 from that point, go up until I hit my graph. That's a step up of 3. That's my next step. And I continue, go over 1 again, go up until I hit my graph. That is a step up of 5. So my steps are 1, 3, 5. Again, we could have gotten that from the equation because the a value is 1. So we could have determined that. The axis of symmetry. The axis of symmetry is this blue vertical line. It is in the form x equals, and what it equals is the value or the x value of the vertex, which is 3. You could also look at what value or what x value is this line going through. And we see that it's going through 3. So that is what x is equal to. That's the equation of our axis of symmetry. The optimal value is just the y value of our vertex. In this case, the optimal value is -4. Our x-intercepts, where it crosses the x-axis. I can see the x-axis here. So where it crosses here, or it's where it touches, and here. So the two x-intercepts are going to be 1, 0, and 5, 0. So those are the two x-intercepts. For our y-intercept, use a different color for that. Our y-intercept, where does it cross the y-axis? Where does it cross this vertical axes, crosses it right there. So that coordinate would be 0, 5. Now, if you're graphing this on Desmos, Desmos does do a good job of putting those key points in gray. So the x-intercepts, the vertex, the y-intercept, those would be in gray, and you could just click on them and they would see exactly what the coordinates are. Right? If you're given a graph, you'd have to make sure that it's accurate and see exactly where it crosses. This one was nice because all the points were given to you, so that would be enough to for you to find them, hopefully. So let's do the same thing with a different equation, and then we'll look at just equations in general. So again, we want to state where the vertex is. So the vertex, I think I did that in red. So our vertex is the highest or lowest point. It's where the axis of symmetry goes through. In this case, it is right here, which is 1, 6. So our vertex is 1, 6. Again, we could have gotten it from the equation, from the h and the k value. Direction of the opening, again, looking for where the opening is. We can see the opening at the bottom here, or where the arrows are pointing. Or you could look at the A value. A value is negative, that means it's opening down, but we can also visually see that. The steps. So if I look at my steps, I start at my vertex, I go 1 to the left or the right, doesn't matter. In this case, we'll go 1 to the left, and we go down until we hit our graph. That's a step down of -2, so our first step is -2. From that point, we go over 1 again, and we go down until we hit our next point, which in this case is 1, 2, 3, 4, 5, 6 down, so -6. So -2, -6. We've dealt with this pattern a lot, or this step pattern a lot. So we might recognize the next step is -10, or because we know the A value of -2, we could use the general pattern 1A, 3A, 5A to actually figure out the other points or the other steps. The axis of symmetry is here in blue. It's going to have the form x equals. In this case, the x value that it equals, if we look, what does it go through? Well, it goes through 1. That's also the x value of the vertex. So the equation or the axis of symmetry is x equals 1. The optimal value is the y value of the vertex. In this case, it would be a maximum, and the highest value in this case would be 6. I just want to make sure I got the right colors. So purple and then orange. So for my x-intercepts, I need to see where does it cross the x-axis. So that would be here and here. So this one's a little bit tougher, right? If I'm looking at the graph, I'm trying to find the x-intercepts. It's not that easy to tell, but we could say it's approximately, it's not quite 3. We could say 2.8 and 0. And for the other one, it's approximately, it's not quite -1. We could say -0.8 and 0. As long as you're estimating approximately, if you're just basing it on the graph. There are ways that you can actually determine the x-intercepts, but we're not going to be looking at that right now. Then lastly, the y-intercept. The y-axis, this is the point that touches, or where the graph touches the y-axis. And in this case, the y-intercept would be 0 for x and 4, not -4, and 4 for your y value. So those are all the characteristics from this graph. Lastly, now we want to do the same thing, identify the characteristics by looking at the chart. So again, it is going to be helpful because all of these are in vertex form. It is going to be helpful to recognize y equals a x minus h squared plus k. So a value tells me if it opens up. In this case, it's positive, so up. Positive, it's up. Negative, so it's down. My vertex is hk. Remember, h is opposite of what we see, so the h value is 5 and negative 17. Here we have negative 4, opposite of positive 4. And then there is no k value, so technically there would be a plus 0, but we don't actually have to show the plus 0 because it doesn't change anything. And then for the last one, I don't see anything in brackets. There's not x minus something or x plus something. So that means my x value of the vertex, or my h value, is 0, and the k is 35. So similar to what we had written, how we showed the plus 0, you could have negative 3 times x minus 0 squared plus 35 if you wanted to actually visualize what it would look like with a 0 in there. But we know that anything subtracting 0 doesn't really change anything. For the jumps are going to follow the 1a, 3a, 5a pattern. A value of 1 in the first one, so just 1, 3, 5. 2 in the second one, so it's going to be 1 times 2 or 2, 3 times 2 or 6, 5 times 2 or 10. And then the last one, a value of negative 3, so we have 1 times negative 3 or negative 3, 3 times negative 3 or negative 9, 5 times negative 3 or negative 15. So that would be the step pattern for that equation. The axis of symmetry, that's that vertical line that cuts in half. It has the form x equals and then whatever the 8x value is of the vertex, or h. So in this case, we'll have x equals 5, x equals negative 4, and x equals 0. The optimal value is just our k value. So in the first one, our k value is negative 17. And if we wanted to add in there, this would be a minimum because the graph is opening up. So because the graph is going to look like this, my vertex is down here. That means it's going to be a minimum value. For the next one, my minimum or my optimal value is going to be 0. It is also a minimum because it opens up. And then lastly, 35 is going to be my maximum. Because it opens down, it looks something like this. So the vertex is the highest point that you could have, and that makes the optimal value the maximum, not the minimum. The very last thing, we're going to look at just kind of a real life scenario, or kind of like a graphical model, or adding a scenario to the quadratic and then answering questions. So so the graph shown below models the path of a ball thrown up in the air. The height is in meters and the time is in seconds. What is the maximum height reached by the ball? Well, the maximum height would be our vertex, this point right here. So 20 meters is the maximum. When did it reach the maximum height? So that we want the time. So when did this happen? Well, this happened right here at this x value, or 2.5 seconds. How long was the ball in the air? Well, if it launches here from a height of 0 and then lands, or has a height of 0, what's that distance? That is 5. So that is 5 seconds. That's how long the ball was in the air. So all this is just looking at is just making sure that we can just read a graph and understand what it's asking us for. In the next one, the path of a ball that was thrown in the air is modeled by the graph. The y values represent the height of the ball in meters, and the x values represent the horizontal distance in meters that the ball has traveled. So what was the maximum height of the ball reached? Again, looking for that vertex. So maximum height of 9. How far had the ball traveled horizontally to reach that maximum height? Again, looking for the x value of the vertex, in this case 10 meters. And what horizontal distance did the ball travel before it hit the ground? So if it hit the ground here, about halfway, so 21 meters, and assuming it gets launched from here, even though that's not on the ground, that's fine, right? If you're throwing a ball, the ball might already be a certain height off the ground. So the horizontal it traveled before it hit the ground was 21 meters. So again, being able to read a graph, understand what it's asking us to find based off of the scenario, and basically it's going to be some of those key properties that we've looked at when looking at a quadratic. So again, just make sure you're familiar with these key properties, right? The axis of symmetry, vertex, optimal value, x-intercepts, and y-intercept.